Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics. We have been discussing the case of cointegration. We have done it in that single equation framework of Granger. Now, before moving to the multiple equation framework of Johansson cointegration, we will first discuss briefly the system of multiple equations in time series analysis and what we refer to popularly as vector autoregression. The basic idea is to give you a feel of what a multiple equation framework looks like over here, so that in our upcoming class we can discuss Johansson cointegration. This is similar to the simultaneous equation models. These simultaneous equation models were structural in nature, as the relationship between variables was determined by the economic theory. As an example, y is equal to c plus I plus g. It is defined by theory. But there are some situations wherein maybe the theory is not sufficient, or a new theory is to be developed, or maybe there is some confusion about what is the exact theory. Take an example. Financial inclusion leads to economic growth. Good. If more and more people are not keeping their cash idle at home and they are keeping it in the bank, then the bank has more cash to give it to the business class or to the entrepreneurs to invest. There will be more economic activity, more income will be generated, more value added, more GDP in the economy. Okay, this logic is fine. But a contrary logic is also there, not exactly contrary, but it moves simultaneously. People will have money to keep in the banks only when there is an element of GDP present in the economy and there is a circular flow in the economy and people are getting jobs and everything is going on in the economy. So, if there is no economic growth, people will not have enough income. If they don't have enough income, they don't have any cash to be kept at the bank, to be deposited in the bank. So, this also looks logical. So, whether financial inclusion leads to economic growth or economic growth leads to financial inclusion, it's not very optimum, it's not very clear that you can say this is leading to this and this is the dependent variable and this is the independent variable. It can be the case where financial inclusion leads to economic growth and economic growth leads to financial inclusion. So that is, there can be what we refer to as bidirectional causality in econometrics. So the philosophy of VAR is, I would refer vector autoregression as will be referred to as VAR in our coming discussions. So the philosophy of VAR is that let the data speak for itself. We do not leave it for the econometrician to specify the dynamics of the model and define that, okay, this is the independent variable and this is the dependent variable. Let the data decide. So in simultaneous equation models, we assume some variables to be exogenous and others to be endogenous. This classification, as we have just discussed the case, can be arbitrary. Also, we need to do identification. If identification is to be achieved by imposing those zero restriction on coefficient of the variables, and that there was a paradox in identification, that identification is achieved by variables which are not present in that equation but is present in some other equation. So nevertheless, so these things were a bit doubtful in the case of simultaneous equation models, which are overcome in the system of VAR. So, Christopher Sims, he said that if there is true simultaneity between variables, they should be treated on an equal footing. That is, there should not be any distinction between which one is an exogenous variable and which one is an endogenous variable. In VAR, there is no distinction between exogenous and endogenous. All are treated as equal. All are treated as endogenous. Further, if you treat some as endogenous and some as exogenous, then the bias of the econometrician or the person who is building the model will be incorporated into the model. And a variable which is exogenous in model may be endogenous in another model. So if you have to introduce more endogenous variables, then we need more and more equations. More and more equations, it will complicate the model, and not only it will complicate the model, but also we will be running into the issues with the degrees of freedom. So in VAR, we just need to consider two things. M, that is, we select variables which are supposed to be interacting with each other, and K, we determine the largest number of lags to be incorporated. If you recall, that can be done through these criterias of AIC, HQ, Hannan-Quinen and Schwarz information criteria or a Kaike information criteria. The basic model of a VAR, a bivariate model we are taking, we are just taking at the moment, there are two variables, xt and we are taking two variables xt and yt. We define them as y1t is equal to alpha plus beta j yt minus j, and it is a summation from j is equal to 1 to k. Again rj xt minus j plus uit. So yt, the dependent variable, is explained by lag terms of the same dependent variable and then other explanatory variables. This equation, since there are two variables over here, we need to incorporate the equation where xt is taken to be the dependent variable. Herein xt is defined as alpha hat, just to separate it or just to show the difference. This is not alpha, this is alpha hat. Alpha was present over here and here we had alpha hat, and then theta j yt minus j. Yt minus j was present in the first equation also, it is also in the second equation, and xt minus j. So xt is being explained as a function of lag terms of yt minus j and also as a function of lag terms of itself. Xt is a function of xt minus 1 also plus the error term. Here we assume that these y12 and y22t are not correlated, as they are they are basically white noise error terms. These are what you can refer to as impulses, shocks or innovations. So this is how you basically present a VAR model. The beauty of this VAR model is what you have seen on the right hand side. Here it was yt, and I just write it in short, there were a few other things, and where we have yt minus say j, and it was xt minus j. There is no xt over here. It means the explanatory variables are only in the lagged forms. There are no contemporaneous variables. So the beauty of this relationship is we can use OLS. We can use ordinary least OLS, as the lag terms will not be correlated with U1t or U2t. So next thing is that If you are using too many lags, it will consume too many degrees of freedom and may lead to multicollinearity. And if we use few lags, it will lead to specification error. Another characteristic is, and this characteristic is also, we will see that it is also a drawback, that we can do this only if xt and yt are stationary. We can do this if only xt and yt are stationary, meaning thereby if your data is integrated at first order, then first you need to convert your data into stationary. You need to convert your data into stationary by the same taking the difference process, but then only you can do VAR. But the issue is, the moment you do that differentiation process, again I repeat the process what it was, say xt it is 2, 4, 5 and 10, then xt minus 1 it will be, say we take this 2 over here, they take this 4 over here, take this 5 over here, then we have xt minus 1. So this is 2, 5 minus 4, this is 1, 10 minus 5 is 1. So if this was not stationary, after doing first order differentiation, we get this as stationary. But when you have to understand this point. We apply VAR not here. We are applying VAR over here. But if you are applying VAR over here, you have differenced the data, you have eliminated all the long run properties. Your data is just a symbolic representation of this year minus the last year. So you have lost all the long run properties. And that is why VAR for an empirical purpose is not of much use. Because the moment you are doing differentiation, normally you will not find, normally economic time series data, they are not stationary at level. If they are stationary at level, you do VAR, very good. But they are not stationary at level, and most of the time series they become stationary only after doing this first order differentiation. So if you want to apply the technique of VAR, if your data is I1, you have to convert it into I0 by this process, and by doing this process you are losing all the characteristics, all the long run characteristics. So if you are doing any analysis on this and you are estimating the parameters, it will not be serving the purpose. And that is the beauty of co-integration. The beauty of co-integration is, we know that the data is like this. We will use this data itself. We will use this xt, although it is integrated at first order, although it is not stationary, we will use this very data to get meaningful estimates. In co-integration, we do not use this data xt minus 1. Only thing is, we need to be clear, or we need to confirm that our data was not stationary at level, but if we convert it with, use the first differentiation process, then we will get a stationary series. We just need to confirm. But when you are working with the data, you are using xt data only. You are using the original data which was integrated at first order, or which is not stationary. So that is the advantage of co-integration. Okay, nevertheless, we are discussing the cases of VAR. So again, we have to be very clear that we can use VAR only if the data is stationary, and if it is not stationary, we need to first convert it into a stationary data. Now, we come to the advantages. See, researchers need not specify the variables as endogenous and exogenous. No need for identification. All variables are endogenous. There is no discretion of the model builder. The person who is doing the research, this discretion is not there. Now, second, variables depend not only on its lagged values, but also on the lagged values of other variables. xt depends upon xt minus 1 and yt minus 1. So in this case, your structure of the model is rich and it's able to capture all the relationships. As a related thing is that when we are having such type of relationship where xt is defined in terms of xt minus 1 and yt minus 1 only, that is on the right hand side we have only the lagged values, there are no contemporaneous terms on the right hand side. So we can apply OLS as lagged values will not be related with the error terms. In simultaneous equation models, a similar type of structure is there, but we cannot use ordinary least squares as it has contemporaneous values on the right hand side over there. Yt is equal to Ct plus It plus Gt. So they are at the same, all the left hand side and the right hand side of the equation, they are all at the same time period. So that is why we need to do their indirect least squares and 2SLS, that is two-step least squares method and all those things. And then we call it Lucas critic, which says that VAR is better for prediction than the simultaneous equation models. So these are the advantages, and in reality these advantages they do as a comparison to the simultaneous equation models. But there are certain disadvantages also. The first is it is atheoretic. It is not backed by a theory. So once it is not backed by any economic theory, you cannot use it genuinely for any policy analysis. Means all of us say, all of us are very well know that you have certain variables which are definitely the independent variables. They are going to impact this, like growth. If economy, carbon emissions will be more if there is more and more manufacturing or economic growth in the economy. So we very well know our energy consumption. We know that when there is more of energy consumption, more carbon dioxide will be produced. It is not the vice versa, that more carbon dioxide production will be there, then energy consumption will be there. So it is rather, we very well know that energy consumption is the independent variable and it is leading to carbon emissions. So in these cases where we have, and there suppose when you do VAR will at one time it will take carbon dioxide emission as the dependent variable, next time it will take energy consumption as the dependent variable, third time it will take income also as the dependent variable, and the other variables will be the explanatory variables. So this is a theoretic and hence suitable, although you can get estimates, but you cannot say that because you cannot apply it to give a possible theoretical foundation of it. Then selection of lag lengths, although we do it by the criteria, but how many lag lengths are to be taken? You are taking xt is a function of yt minus 1 and xt minus 1. How many t minus 1? You will take only t minus 1, or you will take t minus 2 and t minus 3 or t minus 4. This is also an issue over there. Again, you have to estimate lot many parameters. Estimating lot many parameters will always put a strain on the degrees of freedom which you are having. And the one which we have discussed earlier also, all the components of VAR, they should be stationary. If they are not stationary, then we cannot do VAR. We have to first convert the data into stationary, and then we can do this by the process of differencing. So, and we have also discussed that alternatively, if all the variables are co-integrated, we simply reparameterize VAR as vector error correction model and we estimate long run relationship. It's done, and there we don't have to convert the data and only then work on the data. Only thing is we need to just confirm that my data which is first order stationary, which is I1, it will become I0 upon first order differentiation, but we will work with our original data only in co-integration. So these are certain disadvantages of it. Normally in empirical cases, VAR as such is not reported, but when you do not find co-integration, so VAR, not exactly VAR, but some of the things related to VAR are used to get somewhat meaningful interpretations from the model. So before moving to that, I just show you the process. We were going by the same e-views. We have inserted the data. Our data is like this. We have three series, X, Y, and Z. So we go to quick. Then we have estimate VAR. When we estimate VAR, this dialog box opens. We will check the first one, that is estimate VAR. We will see what will be the end. We will just insert all the variables irrespective of what we have thought y is my dependent or x is my dependent. We just enter all the x, y, z three variables in the box of endogenous variables. Then this lag interval, you can again go by the process of here in the VAR itself, you will find the process of lag length criteria, or alternatively you give as many lags as you feel. Normally 4 or 5 is given. If you had given 10 lags or 15 lags, and suppose your data is not of so much length, so and you have so many independent variables x, y, z, a, b, c, d, then the software itself will say that we cannot calculate, you have to reduce the number of lags over here. So once we have done, we will get a result like this. It takes y as the dependent variable, and see what are the explanatory variables: yt minus 1, yt minus 2, xt minus 1, xt minus 2, z minus 1, z minus 2. Means all these are in lag forms. Similarly, next time it is taking your x to be the independent variable, and these are the we are going to take x as the dependent variable, and all these are the independent variables. And these brackets, these last things, they denote t statistics. So if I take this yt minus 1 is significant. It is significant. This one is not significant by the rules of thumb, because it is minus 1.04. If it is less than 2, it will be not significant. This one is also not significant. This is also not significant. This is also not significant. This is also not significant. So we can get this, and also this they will report along with these estimates and their standard errors. The second term over here is the standard error. This is the standard error, this is the coefficient, and this is the this is the probability value. No, excuse me, this is not the probability value, this is the t table, t calculated. Now they also give these things, that is what is the R square and adjusted R square, and these things are also given. So, but I again emphasize, you won't find much of empirical work related to VAR, and even if there are some studies, you will find that they have been supplemented by either Granger causality or impulse response function or variance decomposition. So, to summarize, in VAR all the components should be stationary. If not stationary, we have to make it differencing, and when we are doing differencing, then we are losing long run properties. So we need to supplement the result by Granger causality or impulse response function or variance decomposition. Now we go to Granger causality. You will find that where empirical works of Granger causality are reported, they do not say that X is causing Y. Rather, they quote there that X causes Y in the Granger sense, or they use the word X Granger causes Y. There is a reason to it. See, Granger causality can be said as a variable xt is said to Granger cause yt if yt can be predicted with greater accuracy by using past values of xt than by not having such variables, all other terms remaining the same. So xt is said to Granger cause yt if yt can be predicted with a greater accuracy by using past values of xt than by. So xt is said to Granger cause yt if yt can be predicted with greater accuracy by using past values of xt rather than by not including the history of both xt and yt. So there is that, because of this feature, they do not simply say, empirical studies do not simply say that xt is causing yt or xt causes yt. They say xt Granger causes yt, or they say xt causes yt in the Granger sense when they want to refer to Granger causality. We will do in detail, today we are just introducing the concept, we will do in detail this case of Granger causality. Let us just have a quick view of how it is to be done. We in the VAR only, we go to lag structure. In lag structure, you have this Granger causality or / block exogeneity test. Upon the final process, you will get this result. Now see, here the variable y is the dependent. Let's see x. X, the value, again we use the same rule, 0.05. If this p value is more than 0.05, not significant. If it is less than 0.05, it is significant. So x does not, because the probability value is more than 0.05, x does not Granger cause y. Next, let us take the next variable z. Z, the probability value is 0.06. So at 5%, we can say that z does not Granger cause y. Similarly, let us take, now x is the dependent variable, y does not Granger cause x, and then z does not Granger cause x. Next time, we have taken z to be the dependent variable, y, the probability value is less than 0.05, it is here 0.01. So we can say y Granger cause x. But y Granger causes z. Z is the dependent variable, and x, it does not Granger cause z. So this is how the Granger causality can be incorporated along with the VAR framework. Next, we have another thing which we refer to as impulse response function. Now here what we are doing, we are considering the entire system of equation as a group. I have not written the coefficients, only the variables. This one is the left hand side, and this is equal to, and this happens to be your right hand side of the equation. Now we are considering all the coefficients as a group. If all the groups are significant, then we say that the lagged values of x, yt, xt and zt are important. Here we use F test, which will give an idea about which of the past values are significant, and to determine yt, but we will not give the direction of causality. It will not give whether the effect is positive or negative. Also, it will not give how long it will take for the effect to cause the effect of a cause to die out. Hence, we have to do either impulse response function, or we will see another thing, that is variance decomposition. Now see, what is IRF? That is impulse response function traces out the responsiveness of the dependent variable in VAR to shocks to each of the variables. That is, suppose a unit shock is given to the error term. Impulse response function, it traces out the responsiveness of yt in the VAR to a unique shock in u1t. That is, if a unit shock is given to u1t, what is its effect on yt, xt and zt? Whether the effect is positive or negative, and after how many periods the effect of the shock will die out. If the VAR system is stable, the effect of the shock will die out in the due course of time. But how it happens? This is determined by this impulse response function. Again, we do it in the VAR framework. In VAR framework, you will find this impulse response function. Once you select on this impulse response function, a box will open up. Now it is written here response of y on y. Now let us take response of x on y. Maybe the screen is small, but here it is written response of x on y. So this is 1, 2, 3. This is figure number 4. In this figure, the impulse response function shows that 1% shock is initially creating an impact, but later than the impact dies out and it goes much below. So impulse response function shows that a 1 standard deviation shock in X has first a positive impact on the other systems and then it goes down. Has a positive impact on Y and then the effect goes down and it goes down to a much lower than what was your initial value from where the shock happened. Let us take another case, like say impact of Z on Y. Where is impact of Z on Y? Impact of Y on X. This is Y on X. This is Y to Z, and this is X to Y, and this is X on X. This is X to Z. This is Z to Y. Now see, impact of Z to Y. If there is a shock, there is an initially it goes down, then again there is some recovery, but again it becomes stable. Like if you take this, it is Y to Z. Then when there is a shock, initially there is a downward movement and then it goes up and it fairly rises. So this is what the impulse response function gives an idea of. Next, or the last one, is variance decomposition. It gives the proportion of movements in the dependent variable that are due to their own shocks versus shocks due to other variables. This also we can get from there only, from here. When you go in the VAR, you go to the proc, you will find this variance. If you go in view, you will get variance decomposition, and once you go for variance decomposition, the slide will open up. You will find that this variance decomposition shows that the explanatory variable's strength in explaining the variability in the dependent variable over time. 10 time periods are taken. It shows the forecast error of the variable for each forecast horizon. Like 1, then 2, then 3, then 4. In the short run, that is say in time 1. In time 1, 0% of the forecast error variation is explained by X and 0% by Z, while 100% is the forecast error variance explained by Y itself. The next time at time 2, this from 0 it increases very minutely, 0.25%, and for Z it also increases very minutely, that is 0.28. That is at time 2, 0.25% of the forecast error variance is explained by X, while only 0.28% of the forecast error variance is explained by Z, and around 99% is explained by Y itself. Let us take what happens in the period 10. In this, we can say this is the long run period. In the long run period 10, 13% of the forecast error variance in y is explained by x, and 8%, around 8% of the forecast variance in y is explained by z. The same thing here, we were explaining the forecast error variance of y. You can similarly explain the forecast variance of x and z. So this is how variance decomposition can be demonstrated or performed in our eView software. So to summarize, what we have done today is basically we started with the discussion on VAR. We have seen how VAR is different from your simultaneous equation models. We have seen what are the advantages and disadvantages of VAR, and because of one limitation, that is VAR needs the variable to be stationary. It's not very much applicable in empirical research, and the results of VAR, if at all they are to be used, then they need to be supplemented with things like Granger causality, impulse response function, and variance decomposition. This was the introductory lecture on this. In our future classes, we will see in detail. With this, I call an end to our today's lecture. Hope it was clear to you. Thank you.